Hello everyone, my name is Ivory and I'm a biologist from the University of Florida. Today we're going to talk about soil. What is soil, how is it important, all those sorts of things. So let's start out by talking about what is soil to begin with. Soil is a mixture of three different things: sand, silt, and clay. While they each have different names, all they are is a spectrum of particle sizes. The biggest particles being sand, the middle particles being silt, and the smallest particles being clay. The ratio of these three different types of particles can create different types of soil. For example, here in Florida, we have very sandy soils, while if you go to Georgia, you get the iconic Georgia clay. On top of how soil is mixed together with the sand, silt, and clay, as water runs through a soil, it can create different horizons, which are just pockets of different minerals, such as iron or salts. The combination of the different horizons in a soil can be unique to where the soil is found. Like I was saying earlier about Florida having very sandy soils, that's very iconic to Florida, while that's not iconic to other areas. Let's talk about what makes Florida soils unique. So the state soil of Florida is the Mayaca soil, which is found pretty much all around the state, but is named after a river around the Tampa area. Since Florida soil was created underwater many times throughout history, it's very well adapted to handling water. It can drain water through the soil very quickly. But not all soils are like that. Sand, with its big particle sizes, allows water to flow through each of those cracks. Clay, on the other hand, is very small, and whenever it has water interact with it, it builds it up between all those bonds of clay, and water just stays above it and can very rarely go through it. And so why would that be important? It's important because whenever you're building a home, you don't want clay to be very close to the top of the soil where you build your house, because if you ever get a flood, like hurricanes provide, it can cause your house to flood out. So, if a builder finds this out, they'd most likely build your house on top of sand so that your house has a barrier between you and the clay. So for this experiment, we're testing particle size: sand, silt, and clay, like I said before. So I have 20 grams of soil from here at the museum and 500 milliliters of distilled water. Now, water out of a faucet oftentimes have other particles that are floating around inside of it, and so since I'm trying to check particle size, I don't want those other particles, thus distilled water. To check particle size, I have right here a hydrometer, which can float at different heights, and based on where it's floating at, can tell how many particles are in the water. Alright, so now you can see that this is floating about at the 0 mark. So I want to talk a little bit more about what a hydrometer is and how it works. So a hydrometer has a bulb at the bottom with a weight in it to keep it floating upright. Extending from the bulb is a tube that has increments on it, kind of like a ruler. These increments can tell you how many particles are left in solution. Depending on where the tube is floating in the water, can tell you how many particles are left in the water. The heavier particle is, the faster it falls out of solution, while the lighter it is, the longer it can stay in solution. The heavier particles, the sand, fall out fast, so you do a 1-minute reading on the hydrometer. Since the clay particles stay in solution longer, we do a 6-hour reading to go and see how much clay is left in solution. Since this can handle a liter of water, and this is only 500 milliliters, we have to cut all of our calculations in half. The reason why this experiment works is because sand is bigger and falls to the bottom of the container faster, while silt and clay are smaller, so it takes longer for them to settle. Usually, if you wanted to go and test how much sand, silt, and clay was in a container, you'd measure the sand at about the 1-minute mark, and then you test for clay at the 6-hour mark. And then the subtraction of both of those gives you how much silt is there. As I said previously, Florida soil is pretty much just sand with a little bit of silt and clay. So there's not going to be too much movement on the hydrometer, but you'll still see a little bit. Now that I've added the soil into the cylinder, you'll see it's floating around the 10 to 20 grams per liter of clay and silt. The sand has fell to the bottom at about the minute mark. As time passes, you'll notice more of the silt will fall to the bottom, and the hydrometer will read less and less as time goes by. A few hours have passed now, and the hydrometer is consistently reading about 5 grams per liter. So now that we're pretty much done, let's see what this means for our results. Since this is only a 500 milliliter cylinder, we need to cut all of our numbers in half. Okay, so let's put this all together. At the 1-minute mark, 10% was still floating around in solution, while 90% had already fell out, which means that 90% was sand. Now that all of these hours have passed, all of the silt has now fell out of solution. And so since we're getting a reading of 2.5%, that means that 2.5% of that soil was clay. Since we know this soil was 90% sand from the first hydrometer reading and 2.5% clay from our most recent reading, subtract the two from 100% and that gives us 7.5% silt. While this soil type is pretty common in Florida, it's by no means the only type. Within Florida there's hundreds of different named types of soil and probably more that are unnamed. A lot can be told about the environment based on its soil. For example, I can tell what crops are grown in an area based on what nutrients are left in the soil. Or I can tell how much rainfall an area gets. I hope you enjoyed my lesson. If you have any questions or would like to perform this experiment in your school, please reach out to the email below.